Hello and welcome to the second lecture of week 9 of the course Introduction to General Relativity. In this lecture, we will arrive at the Einstein field equations, which are the equations of motion for the gravitational field. Important milestone result as far as this course is concerned. Now, like the previous lecture, this lecture will be also of an hour duration, or a bit less than that, and hence it is to be split into two parts on the NPTEL website. So the references for this lecture are the following: Carroll's lecture notes, chapter 3, these pages, and chapter 4, the following pages. Nakahara's book, chapter 7, these sections, and I'm also going to follow Nakahara's convention. Please be aware of that. And the lecture notes will be posted on the NPTEL/SWAM website as usual. All right, let's look at the agenda for today's lecture. First, I will discuss some contraction or trace of the Riemann tensor. And because the Riemann tensor has 4 indices, one can take the trace in a couple of different ways. But it'll turn out both of them give rise to the same quantity, which is called the Ricci tensor. Okay. Upon contracting a second pair of indices, we get the Ricci scalar. So we will discuss these. These are important because they play a crucial role in the Einstein field equation. We write the Einstein field equation in terms of the Ricci tensor and the Ricci scalar instead of the Riemann tensor. Then I will discuss the Einstein field equations and we will give some motivation of this result. Next, I will change the equation by introducing something called a cosmological constant, and we will see a natural reason why this cosmological constant should be considered. And finally, we will discuss the Einstein-Hilbert action, an action which you can extremise and get to the Einstein field equations. Let's discuss the first item in our agenda, that is contractions of the Riemann tensor, namely the Ricci tensor and the Ricci scalar. Now, let's recall what the Riemann tensor is. It was introduced in the last lecture. So this is how the Riemann tensor looks. So as you can see schematically, the Riemann tensor consists of 4 terms. 2 terms are of the type where you have derivative of the connection, and 2 terms which are quadratic in the connection. Okay, del gamma and gamma square type terms. And I've displayed only 2 terms because the other 2 terms can be written down by swapping some indices, like swapping rho and sigma. As you can see here, if you swap rho with sigma, you can write down the other 2 terms from the first 2 terms. Okay, and then, as I said, we will also often write the Riemann tensor with all the indices lowered. Now, in the original definition, one index was a 1 common free rank tensor, so 1 index was up and 3 others were down. Most of the time, often we will use the Riemann tensor with all 4 indices downstairs. That is a 0,4 tensor by using the metric to lower the upper index. All right, the connection we will take to be Levi-Civita, as I've mentioned before. The preferred connection in general relativity is the Levi-Civita connection. And if we would take the Levi-Civita connection, we went through the math. The number of independent components of the Riemann tensor is actually d squared times d squared minus 1 by 12, where d is the number of space-time dimensions. All right. Now, as I said, the idea is to learn about contractions of the Riemann tensor, and there are 4 indices. We cannot contract the first 2 indices, right, mu and nu, because we know that the Riemann tensor is anti-symmetric under the swap of these 2 indices. So if I contract R mu nu rho sigma by G mu nu, the inverse metric, then as we know, G mu nu is symmetric in mu nu, but R mu nu rho sigma is anti-symmetric in mu and nu. So this contraction will actually be 0. Okay. So it doesn't make sense to contract the first 2 indices, and ditto for the last 2 indices, because again, they're anti-symmetric under swap. But if we try to contract with G rho sigma, they will vanish. The whole entire thing will vanish. So the only choice is you can contract in the first and the third index. So this mu and rho. Now, because of the symmetry properties of the Riemann tensor derived from the Levi-Civita connection, it doesn't matter whether we contract between mu and rho, the first and the third, or nu and sigma, the second and the third, because of the symmetry properties of the Riemann tensor. It's very easy to show that the result will be the same, okay, because of the antisymmetry properties. R mu nu rho sigma is equal to mu mu, where I've swapped mu and mu, and then we can also swap sigma and rho. Okay, and then you can see if I contract the second, first and the third, it gives you mu rho with the second and fourth. Okay, first and the third, before it will be the same. As you can see, if I contract mu and sigma, so contracting the second and the fourth is same as contracting the first and the third. All right. So it doesn't give you any difference. So we will contract the first and the third, and that contraction is called the Ricci tensor. Okay. As you can see here, I've contracted the first and the third index. As a result, now the new tensor has two indices, R sigma nu, and this is called the Ricci tensor. It is thought of as a trace of Riemann tensor. Okay. And it can write the formula in terms of the connections, but it is not that illuminating, so I'm just leaving it at ellipses. You can always contract mu and nu in these formulas. You can set mu to equal to nu in these formulas and obtain the explicit form. But as I said, it is not that illuminating right now, so we will not display it. Now, because of the pairwise symmetry of the Riemann tensor, remember Riemann tensor has symmetry under a pairwise exchange of mu nu with rho sigma. So R mu nu rho sigma will be same as R rho sigma mu nu. The rho sigma index swapped with the mu nu index, right? Because of the pairwise symmetry of Riemann tensor, one can show the trace of Riemann tensor, that is the Ricci tensor, also has the symmetry property. R mu nu equal to nu mu. Okay, R mu nu equals R nu mu. So it's a rank 2 symmetric tensor, and the number of independent components of Riemann tensor can then be easily obtained. If you're in d space-time dimension, this is the d by d matrix, which is symmetric. The number of independent components is d times d plus 1 over 2. Okay, so these are the number of independent components of the Ricci tensor. Now, the Ricci tensor has indices. You can further contract these two indices with the G mu nu. This is what I've done. G mu nu contracted with R mu nu, and you can get a traceless scalar object, which is called the Ricci scalar. This also plays an important role in general relativity, or some people would call it the scalar curvature. All right. So before we proceed with the Einstein field equation, let me just mention this, that one can decompose the Riemann tensor into trace pieces, which are indicated in blue fonts. For example, the Ricci tensor and the Ricci scalar. And, sorry, this is a typo here. A traceless piece, which is indicated in red font. Okay, this is the traceless piece is called the Weyl tensor. As you can see, the Riemann tensor I've written with the traceless part, and then the blue ones are the trace parts because they involve the Ricci tensor and the Ricci scalar. Okay, so the traceless part is called the Weyl tensor, and it shares the same antisymmetry or symmetry properties of the Riemann tensor. That is, the Weyl tensor is also antisymmetric under the swap of first two indices, and it is antisymmetric under the swap of the last two indices, and it has this pairwise symmetry. That is, if you swap the first two indices with the second two, it is symmetric. So the Weyl tensor, in some sense, satisfies all the symmetry / antisymmetry properties of the Riemann tensor. The difference with the Riemann tensor is that the Riemann tensor has a non-trivial, non-zero trace. On the other hand, the Weyl tensor is completely traceless. Okay, any contracting any pair of indices kills it. And as it is obvious from the definition that because of these factors of d minus 2 and d minus 1 This decomposition is, this formula for the decomposition is not well defined in d equals 2 or d equals 1. That is just one time in one space, one time dimensions. This formula is well defined only in d greater than 2 dimensions. But it turns out even in d equals 3 dimensions, the Weyl tensor is 0. It is 0 even in d equals 3. And the reason is kind of simple. In 3 dimensions, the number of components of the Riemann tensor, if you use that formula, d square minus d square times d square minus 1 over 12, you get the number to be 6 by 12. If you plug in d equals 3, you get the number to be 6. So the number of independent components of the Riemann tensor is 6 in 3 dimensions. And the number of independent components of the Ricci tensor in 3 dimensions is also 6, because it is given by d times d plus 1 over. Which in 3 dimensions, d equals 3 is also 6. So the number of components of the Ricci and Riemann are the same. Hence, there is no degree of freedom left in the faceless part of the Weyl piece. Okay, so the Weyl tensor is strictly defined for d greater than 3, the 4-dimension onwards. Now, you can ask, what is the significance of the Weyl tensor? Why do we care about it? And it turns out that the Weyl tensor physically measures tidal distortion of shape, but not volume. Remember, if I take an extended object in a gravitational field, because the gravitational field varies over the extension of the object, there will be tidal forces, and as a result, the object will get distorted. It will get laterally contracted and longitudinal stretching. So Weyl tensor measures how the shape gets distorted, but not the volume. So during tidal distortion, the volume can change as well as the shape can change. The Weyl tensor is actually something which captures the change of shape, but not the volume. So the Weyl tensor is invariant under local rescaling with the metric. That is, if I consider two metrics, g of x and g tilde of x, which differ by this scale factor, omega square x, which is a function of x. So we consider two candidate metrics for the same space. One is g and one is g tilde, and they vary with, they are different from each other by scaling omega square. Then you can show that the Weyl tensor for these two metrics are the same. Okay, the Riemann tensor for g and g tilde will be different, but the Weyl tensor corresponding to g and g tilde will be the same. Okay. An important negative information is that the Weyl tensor vanishes from maximally symmetric spaces. Remember, some time back when we discussed Killing vectors, we introduced the idea of maximally symmetric spaces, which have maximum amount of Killing vector, maximum number of Killing vectors, and they correspond to Minkowski space, de Sitter space, or anti-de Sitter space. If you're in Lorentzian signature and in Euclidean signature, they correspond to Euclidean hyperspace, the sphere, and the hyperbolic space. Now, so the Weyl tensor vanishes for maximally symmetric spacetimes because the maximally symmetric spacetimes can be written as rescalings of flat space. So these geometries, maximally symmetric geometries, are sometimes also called as Weyl flat geometries. Okay, Weyl flat. All right, so this is an aside, but let's get back to our object of interest, which is the Ricci tensor and the Ricci scalar. So we want to write down the equation of motion for the gravitational field. Remember what the exercise we did while discussing Diffeus-Pauli gravity is that we start with the Newtonian gravity, which is non-relativistic, and to write down a relativistic version of this formula. So in relativistic physics, the mass density rho is replaced by T mu, the stress energy momentum density tensor, and the equation which we obtained was called the Diffeus-Pauli equation. This is what I have it here, equals to this second LHS. You can see it is second order in H, the Diffeus-Pauli field, and the right hand side is kappa T mu, where kappa is minus 16 by G Newton over C cubed. I'm sorry, G Newton has got truncated in the space, but there is G Newton here. Now, H 0, the 0 component of H is related to the usual Newtonian potential by this formula, and we highlighted this before. This factor of c squared is just for dimensional reasons because H is dimensionless, and we know the Newtonian potential has dimensions of velocity squared, so phi over c squared is dimensionless. And this -2 factor is for convenience later, and which we motivated that H mu will turn out to be perturbation of the geometry. So that's why this -2 factor was put in. Now, this equation has an associated internal gauge symmetry. That is, instead of H, if I consider it H prime, which is related to H by in this way, that is H mu minus del mu lambda nu of x minus del mu lambda mu of x, while lambda is a completely arbitrary vector field, then H prime also satisfies this equation. So physically, we cannot distinguish between H and H prime. Both of them satisfy the same equation, so both of them represent the same gravitational field in this sense. And the equation tells you that there are multiple ways to represent the same gravitational field. There is a lot of arbitrariness in the description, or redundancy in the description. Next, if you remember, what we try to do in Fierce-Pauli is to couple it to matter. Now, if you try to couple it to matter consistent with this gauge invariance as well as other principles, then it turns out that in addition, this gauge symmetry, which was an internal gauge symmetry, trying to couple it to matter, for example, the point particle, which is what we discussed, you need to also consider transformation of the space-time. So the internal symmetry gets transformed into a space-time symmetry, x prime going to x plus lambda. And as a result, this internal gauge symmetry now reads something like this. So the difference between this line and this line is that the argument of h prime is x here, but the argument of h prime is x prime here. Okay, so consistent coupling to matter forces the symmetry to be converted into a space-time symmetry, space-time gauge symmetry, and it also forces us to consider the metric of space-time to be not Minkowski, but Minkowski plus some perturbation, which is caused by the gravitational field, H mu, the Fierce-Pauli field. Now, this procedure we only did up to first order. If you remember what we did, we only did the first order in H. But you can ask what happens in the next order and so on and so forth. So, of course, this process can be extended order by order in H. So one can construct order by order corrections. And then the Fierce-Pauli equation will also change by having higher order correction, order h square correction. Okay, one can pursue this procedure and write down the form of the equation. And this order by order construction will of course give me an infinite series, which we have to then resum. And this is a very laborious process, which is not very insightful. It is very elementary because we're doing order by order, very simple. But at the end, remember, we have to sum that and sum everything we get. So this is not a very economical process. Okay, and neither is it economical, nor does it provide much insight. Okay, so instead of doing that, we will adopt a different strategy to obtain the field equation, which is we will directly construct a nonlinear generalization. So we know that coupling to matter forces this Fierce-Pauli equation to change by inclusion of higher order terms, quadratic, cubic, all that. So instead of doing it perturbatively order by order, what we will do is directly write down a nonlinear generalization of the Fierce-Pauli equation, which is the tensor equation under general coordinate transformation. Okay, so we will consider some tensor equation. Let's say A mu equals kappa tau. So we will directly write down an equation, a tensor equation, which is tensor under general coordinate transformations. And A will be made up of it's nonlinearly dependent on H. Okay, directly write down. And as I said, the eta and H can be combined into G mu. And under general coordinate transformations, we know how the metric transforms. This is how it transforms. X goes to x prime, which is a function of x. then G mu will go to G prime mu of x prime, which is given by this formula. So we will directly write down a nonlinear generalization of the Pierce-Pauli equation, which will be a tensor equation, and it will be invariant tensor equation under these coordinate transformations, general coordinate transformations. So the right hand side, as I mentioned, is proportional to kappa T mu nu. It's kappa T mu nu, so it is already a tensor in the general coordinate transformation. Nothing to alter there. But the left hand side, we must have a tensor with two free indices, because the right hand side has two free indices. The left hand side should be symmetric under swap of mu and nu, because the right hand side is. And as we can see from the Pierce-Pauli equation, it must be second order in derivatives of g. Remember, we're not using g and h, I'm sorry. It should be second order in g, because the Pierce-Pauli equation is second order in h, and h is defined to be the difference between g and eta. Okay, so second order in g means second order in h, at least to leading order. But g, as I said, that is the nonlinear version of eta mu added with h plus higher order correction. All right, so we have an obvious candidate, which is the Ricci tensor, right? We know the Ricci tensor is made up of second order derivatives of g, because the Ricci tensor is made up of the Riemann tensor, contractions of the Riemann tensor, and the Riemann tensor is made up of derivatives of the connection del gamma, and gamma we know has first order derivatives of g, so del of g. Second order derivative in g, it has two indices, and it is symmetric. By construction, the Ricci tensor is symmetric if we use the Levi-Cavity connection. So it seems like R mu has all the qualities we are looking for. So maybe the first guess in the field equation is R mu equals alpha T mu nu, where alpha is some constant. But this is actually what Einstein wrote as his first guess as well, just as we are guessing it. But it doesn't work. The reason is, remember, T mu nu is covariantly conserved, so there's a conservation law for T mu nu. It isn't compatible with conservation of energy, because if I take del mu of both sides, this will vanish, covariant conservation of energy, but this will not vanish. Okay, one can compute the divergence of R mu nu, and in general, it doesn't vanish. On the other hand, del mu to mu nu always vanishes, regardless of what is the configuration of the matter. Del mu to mu nu is always 0. But del mu of R mu nu is not necessarily 0. And this can be shown from looking at the second Bianchi identity. Of course, I haven't introduced the second Bianchi identity. I only introduced the first Bianchi identity while discussing properties of the Riemann tensor. But one can also write down another Bianchi identity, which is called the second Bianchi identity, in which we take lambda mu rho sigma derivative, and then cyclically commute this derivative with rho and sigma, the last two, cyclic permutation, cyclic forms. Of lambda rho and sigma. So it will give you two more terms. This is equal to 0. So this is called the second Bianchi identity. And if you contract mu with rho, you get a Bianchi identity for the Ricci tensor, which looks like this. Okay. So please refer to the notes which will be posted, where the details of the derivation can be found. Now, I can rewrite the right hand side as follows: half del nu or Laplace sub nu of R equals, I can use G mu nu to raise this index to mu, which I have done here. And then, because we are using the Levi-Cavity connection, the metric will be covariantly constant, so I can push it inside here. from outside, I can put it here because the Levi-Civita connection will not take the derivative of the G is 0. So G behaves like a constant. I can pull it from the left to the of the covariant derivative to the right of the covariant derivative without any issues. So this right hand side I've been able to write as a total to the covariant derivative of F nu. Now if you look at the left hand side and the right hand side, both are the mu covariant derivative del mu. Okay, mu covariant derivative of both sides, and hence I can bring this over to the left hand side, combine with the term on the left hand side, and we get some equation which looks like this: del mu of G sub mu nu equal to 0, where G sub mu nu is r mu nu minus half this minus this. Okay, r mu nu minus half G mu nu r. So this combination, which is divergence free, is called the Einstein tensor. Okay, this is called the Einstein tensor. After Einstein, who figured it out. So it's symmetric because it is made up of the Ricci tensor and the metric tensor, both of which are symmetric under swap of mu and mu. It is divergence free because the divergence vanishes due to the second Bianchi identity for Ricci. And it also, because it is made of r mu nu and r, it consists of second derivative of the metric. So now we can look at the consider equation. Instead of r mu nu equals alpha t mu nu, we can consider G mu nu equals alpha t mu nu, and this would be consistent with covariant conservation law for energy because del mu of both sides will vanish. Okay, so this is the Einstein field equation. G mu nu equals alpha t mu nu, and what the only job that remains to be done is to figure out what this constant alpha is. In the Pierce-Pauli we had this kappa, so it must be related to this kappa somehow. And the way it is done is to linearize the G mu nu in terms of H mu nu, which we will do in the next lecture when we discuss gravitational waves. So determine alpha by looking at the weak field limit. That is, write down G to be eta mu nu plus H mu nu and linearize G mu nu in H powers of H. This will give you back the Pierce-Pauli equation, and from that you can read off alpha in terms of kappa. Okay, and it turns out alpha will be equal to 8 pi G Newton C to the 4th divided by C to the 4th. Okay, so now that alpha is determined, we can write down the field equation. Instead of G mu nu, I've written its expanded form: r mu nu minus half G mu nu r equals 8 pi G Newton over C to the 4th C mu nu. Okay, so this is the Einstein field equation, which tells you how matter curves geometry. So there's matter, and the left hand side is made up of curvature parts, so it tells you how it is an equation which shows how matter curves geometry. Okay, now as I said, this r contains second order derivative of G, and of course our expression for r is extremely nonlinear. It should be obvious. Let me go back to yes. As you can see, the Ricci, the Riemann tensor contains this gamma square pieces, so it's nonlinear because each over one will have factors of G and del G, derivative of G, so it's a highly nonlinear equation, which is second order. Okay, and how many equations are there? Well, r mu nu is a symmetric tensor, and so that gives you d times d plus 1 by 2 equations. And naively you might think that, well, this is pretty good because I need this many equations to solve for the metric, because the solution of this would be the G mu nu, and the G mu nu is also a symmetric tensor just like r mu nu, and it has same number of components. So maybe G mu nu gets uniquely determined by these equations, but that is actually not the case, because remember, there is the Yankee identity, okay, not all components will be independent, and one has to satisfy this Yankee identity, which imposes the number of constraints. Okay, so maybe not all the components of the metric will be determined, because the total number of equation now is d times d plus 1 over 2 minus d, which will be d times d minus 1 over 2 instead of plus 1 over 2. So this many independent components, independent equations you should get from the field equations as well as the Yankee identity. Now you might be concerned that this is less than the total number of components of the metric, which is d times d plus 1 over 2. So will the metric be determined or not? And the answer is, well, in some sense the metric components, these are also not everything, because we can do diffeomorphisms, and by doing diffeomorphisms we can set certain number of components to 0. Remember, there are d coordinates, so we can perform coordinate redefinitions of the d coordinates and turn off d components of the metric. Okay, so the first line is that not all components of the EFE are independent. Einstein's equations are independent because of the Yankee constraint. In fact, these are the total number of independent constraints, and this is equal to the number of mu modulo diffeomorphism. Because remember, I can do d coordinates. There are d coordinates, and I can do coordinate redefinition by doing diffeomorphism, and by doing d set coordinate redefinitions, I can set some components, in fact, d components of the metric to 0. So it's okay. There is an exact match between the number of independent equations and the number of independent degrees of freedom.